Hello everyone, and welcome to this video short where we are going to talk about and introduce the general matching problem and also talk about the concept of reductions, that is reducing one problem to another problem, a very common practice in computer science. And to start off our example today, we're going to look at using a bipartite graph to structurally diagram out the general matching problem. So first, a bipartite graph is a graph where we can separate the nodes into two different node sets, just like here. So in these two node sets, we have nodes that are dog lovers and nodes that are dogs. And the idea here is that we want to match dogs to their dog lovers. And we have used a graph to identify which dog lovers might be best matched with which dogs, or might be open to taking on those dogs as pets, let's say. And so if there's an edge that exists between the dog lover and a dog, indicates that they are a viable match, whereas if an edge does not exist, then they wouldn't be a good match, let's say. So here the graph, all right, the edges in the graph are used to represent the relation, whether the dog would be a good match for that particular dog lover. All right, and so this bipartite match, or this bipartite graph, is again identifying this matching problem scenario here. So our job here in this matching problem is to identify a match of dogs to dog lovers. Right? And so here is one such match, right? There's all sorts of different matches that could occur here given the possibilities. So one match would be that we could assign, let's say, the first dog to the first dog lover, and the second dog to the second dog lover, third to the third, right? However, in this matching, note that our fourth dog doesn't get to get matched, and our fourth dog lover as well is left out. So this is a particular matching. It is a valid match, but it is not maybe the best match possible because, again, one dog and one dog lover are left out. So we can investigate all different combinations of matchings possible to see if we can get one where everyone gets paired up, right? That would be a maximal matching or an optimal matching. And so again, looking at this particular example, we see that, well, this particular dog number 4, only has one possible match, and that's dog lover number 1. So if we were to switch that, that would free up dog number 1, who could get matched with human number 4, dog lover number 4, and so that would actually give us a better match, meaning that all 4 of the dogs are matched, right? And all 4 of the dog lovers are assigned as well. So here's an example of a match, the general matching problem, examples of different matches, and then a maximum or optimal matching given that. So again, this is a great, another great example of where we can use graphs to solve a general problem. This is a matching problem. Now, one really interesting thing to note here is that we can solve this problem using a problem solution pair that we have investigated previously, specifically looking at flow networks and finding the maximum flow. So how can we do that? Well, if we take our bipartite graph, we add a source and a sink, right? And we simply assign an equal flow or equal capacity to each of these edges, just to indicate that we can assign one dog or one person to one dog, right? Then we can map this into a maximum flow problem, meaning that if we want to find a maximum matching, it is analogous to finding a maximum flow given this new graph structure where we have added the source, the sink, added capacities, simple ones in this case because the idea is we just need to match 1 to 1. So we have simple capacities on all the edges here. And so now we just solve this matching problem by solving the max flow problem. All right, this is great. And so this particular scenario here, now we can see that we have our flows. The flow is analogous to the match or the assignment process here, shown on top of the capacities. And so our max flow is in fact 4, so we have an assignment for all 4 of our puppies. This concept of taking an existing problem and reformulating it or transforming it into another problem for which a solution already exists, such as taking our matching problem, changing it into a max flow problem where we already have existing max flow algorithmic solutions that exist, is referred to as a reduction. That is, we reduce some problem A into some problem B, and then we can use problem B to solve problem A. Right? A very popular strategy used in computer science to solve complex or difficult problems. This is also an interesting algorithmic solution to solving data analytics problems, right? Especially if we're trying to do some sort of analysis, right? If we can change our data model or change the problem scenario for our data science problem into some version of another problem or an instance of another problem for which we have all of these different analytic tools that exist, all these different algorithmic solutions that exist, we can, again, reap some really great benefits, get some really interesting information out of that transformation. And so this is the concept of reductions. And so I encourage you to continue through this slide deck, look at a couple of the examples of reductions here. And again, we will learn to apply this to a few of our data science problems that we'll be presented with in class. All right, well, thank you for joining me in this video short, and I'll see you in the next episode.